Thank you, Atul, for organizing this, and thank you for having me here. So this is part of our work in collaboration with Zishan Ahmed, Professor Subhadeep Mitra, Professor Sh Shantanav Chakravarti, and I'm presenting some early fault-tolerant methods to simulate open quantum systems. So I would prefer if you you can feel free to interrupt me for questions, and I've divided my presentation into four sections. So I'll also stop in middle to clarify things. And so first I'll cover some preliminaries. So I'll describe what open quantum systems are, and then I'll describe collision models, which is like the main framework that we have used, and then I'll describe our algorithms. So usually in quantum systems, our main question is how does a quantum system evolve, and how can we simulate their evolution? So the problem at hand is someone has given you a quantum state, some description of some system, and you want to find the state after some time, let's say t. And one can solve this using or by solving the Schrodinger equation. So if you have a isolated system, and we are assuming here that the system description doesn't change, so it's a time independent Schrodinger equation. So one can solve this, and this will result in a unitary dynamics. And there are a plethora of methods to simulate these unitary dynamics on quantum system. Depends on how the unitary is described or what resources you have, and yada yada. So what we are dealing with today is a bit more complicated. So the thing is this picture of solving Schrodinger equation is incomplete. No quantum systems are perfectly isolated. So there's always some environment, some noise present. So what we actually need to simulate is an open quantum system. But usually the environment is pretty hard to characterize, or we at least don't care much about it. So what we are dealing with is description of the system, but the system is in presence of some environment. It is interacting with the outside world. So for the whole time, so the trivial way to do this is take both system and environment into account, and then build its dynamics, and then just remove the environment. But this is not efficient, because the environment could be huge, and you don't know how to characterize it very properly. So what we want is a reduced dynamics of the system. So at each point we are only tracking the evolution of the system, but there is some interaction with the environment present. So for this, you basically need some different formalism. So you in closed systems, you only deal with pure states, but you have to cause you are removing the environment you're tracing out. There will be some classical probabilities involved. So you'll have to use the density matrix description, and then the evolution will not be unitary in general, and it will also not be reversible. But how will one describe this dynamic? So in the closed picture, one can use the Schrodinger equation. Is there any parallel to Schrodinger equation that I can use in the open quantum systems? So the answer is it depends on how you characterize the environment, or what kind of environment and environment interactions you're dealing with. So for our purposes, we will put some constraints or assumptions. We'll take some assumptions. These are pretty standard, and in most cases, people usually work with these. So namely, there are three assumptions that we are taking. First is called Born approximation or weak coupling approximation. So we are assuming that the system interact very weakly with the environment, and at every stage I can basically write it as a separable states. Another assumption we are taking is there is no memory in the environment. So uh, it could mean that the environment is very huge or the dynamics of the environment is very fast compared to system. So any information that goes in the environment get lost. There is no information that flows back into the system. Third is called rotating wave or secular approximation. What it basically means is we only care about the resonant frequencies. So like any non-resonant or fast oscillating terms, we if we like approximate over a long time, goes away or it becomes zero.
Right. So
So
sorry, I have a few questions already at this point. So I'm not very familiar with open systems. So if I understand well, this weak coupling thing that you're saying, I thought it had more to do with the size of the environment, because you're saying that weak coupling ensures that the system doesn't significantly alter the huge environment. And I
it
always
does.
thought that it doesn't affect it because the system is huge and not so
It
much
does.
because the
Yeah.
coupling.
So you can have weak. So you can have Born approximation. And I think like both the ways. I'm not 100% sure if like both are like needed or uh, like if you can replace one with another. But usually, uh, so what fundamentally it means is the environment doesn't change a lot. So there is no like at each time step the environment remains constant, and
Right.
you
That's
can
why you
achieve
also
this
need
either
to.
by making the environment huge or at least like making the coupling very weak.
Okay. Okay. I guess no memory is also needed for the same reason. You know, you're making basically using the same environment at every step.
Yeah, but
Right.
like in some ways I can also have a memory along with weak coupling, like if I somehow like engineer it so that way, like for our case both are needed and like one is like separate from other.
I see. I see. And this last one is very mysterious. So, what are the waves here? What when you say resonant frequency of what? What should I? How do I understand this? I'm not fully sure I follow.
So if I give you an analogy, like let's say like you're uh, taking a pendulum, say like your system is pendulum and like you are interacting it with some external drive, and so like you can model the like so there will be resonant frequencies which will like couple with the frequency of the oscillator, and then there could be non-resonant terms, and usually you will get terms like let's say you have two frequencies omega 1 and omega 2, and you'll get terms like omega 1 minus omega 2. So if omega 1 and omega 2 are like uh, similar, then only if you integrate it over like long time, those terms will only survive. And if they are like drastically different, so delta omega is used, then these terms become zero. So
Mhm.
these are like it in some sense it also means that you're only taking let's say like second order approximations, or like higher order terms will have like faster rotations, and
Yeah,
you
but the
can.
analogy is a little. I'm not. Yeah, I mean, I know what it would mean. I guess in the existence where there's clearly a notion of driving and resonance and all this, but in this case, it's not very clear to me, right? Because you're coupling to some environment, and I don't know what, like, for example, if I give you a Hamiltonian, right, and that's coupling to some, sorry, it's coupling to some environment, right? You can ask as well afterwards. If you're coupling to some environment, right, then how do I think about resonant frequencies? Is there like a Like suppose I give you a Hamiltonian, right? Like some system Hamiltonian, and I give you some, I don't know, interaction with the bath or whatever. Right? Like you're thinking. From this, how do I figure out what I would call resonant frequencies and what I wouldn't? Is that clear? Or
It's not like exactly that. So I think like one will have to like go into like derivation of the Lindbladian. So
I see.
to like get a like better picture, but um, basically like when you put these first two approximations, you get a Redfield equation. And the Redfield equation, the terms in that also depend on time. And to make this completely time independent, you have to take the secular approximation to remove the. So basically, the uh, the resonant terms will be the mean deviation or like how the system is changing, and then the non-resonant terms are like small fluctuations. So you need to average over them to get a simpler picture.
and all of these are functions of the interaction and the Hamiltonian.
Yeah.
Right. Okay. Thanks. So you can ask your question. I think it's good. Okay. Tell him that.
Yeah, you can continue. Thank you.
So this is usually how one write a Lindbladian equation. So there are two terms in it. So first term is very familiar. So if you just ignore the second term, it becomes a von Neumann equation, which describes the closed system dynamics. And the second term is the thing which describes the dissipation or the interaction with the environment. So all the information of the interactions are basically present in these operators LK, which are called jump operators or Lindbladian operators. And these describe how the system is interacting with the environment. And gamma is called decay rate. So like if you increase the gamma, the contribution of the environment will increase, and like there's a faster or slower dissipation. Now, apart from simulation,
Sorry. So it's called dissipation because it's decohering or it's losing energy.
It can do both.
I see. So why can't it inject energy if you're interacting with the environment? I would have imagined that you could potentially also inject energy. Why aren't those terms present?
You can have energy also, like it can also get the energy. So I think dissipative is like normal term like commonly used, but I don't see why you can not get energy from the like environment. That is also
okay, it's included. You're saying.
Yeah.
Okay.
Yeah. Question.
Yeah.
Is there any relation between these LKs and like the Krauss operators of the CPTP map that you're applying?
Yeah. So one can there is a Choi-Jamalkowski isomorphism, and one can use that to get a Krauss map from the jump operators or vice versa. So there is a direct dependence on that. But I think the Krauss map is more general. So like when you do a Krauss representation, like you don't put all these assumptions there.
Right.
So apart from quantum simulation, there are recently people have found more use to the Lindbladian dynamics. So first is if for some constructed Lindbladians can take you to the Gibbs state or ground state. So basically, you can think of it as you are connecting your system to let's say a thermal bath. So eventually it will get equilibrated with the environment and your system will become a thermal state. Now, one can also find Lindbladians whose stationary states are thermal states and then show that the system thermalizes fast enough. So, for particular systems, people have used the Lindbladian dynamics to prepare either the Gibbs state or ground state. And recently, there have been some more work to use Lindbladians for other applications. So, particularly one, so Lindbladian has it's basically a differential equation, and one could encode other kind of differential equations in the Lindbladian form, and then use a Lindbladian dynamics to probably like solve those equations. So, just to motivate that it's much more than quantum simulations. So now our task becomes a little bit more complicated. So one will give you a Hamiltonian, which describes your system, a set of jump operators, some initial state, and I now ask you to simulate these dynamics, let's say for some time t, and with some epsilon precision. So this is what our goal is for today. I think I can stop for a second for questions. Okay, so I'll describe another kind of open quantum system picture or formalism, which is like more intuitive or it's a bit abstract but more versatile. So it is called collision models or repeated interactive models. So what it does is describes the dynamics in a discretized way with a macroscopic picture. So instead of solving a differential equation, what we have is a system which is colliding with some environment. And then the dynamics is derived by these collisions. Now, one can tune how the collisions are happening or like what changes the collision bring and stuff like this. Now, so if I describe the good part about the collision model dynamics is very intuitive. Plus, it is also mathematically easy to work with, and you can also see a implementation of it. So if I describe one collision, what we have is a system and a small environment part which comes and interact or like collide with the system, and it brings some delta change to the environment. Oh, so sorry, system. And then you forget about the system. So mathematically, I can describe it as you started with some system, you attach the environment to it, and then the interaction is described by some unitary acting on the joint state, and then you trace out the environment. Now, if I design or describe you what these unitaries are, you can basically build a quantum circuit out of it. And this is what I'm waiting for you.
Yeah, sorry, I was struggling to get the thing. Okay, right. So I just wanted to quickly check that in this collision model that you're describing, the environment size is constant.
It doesn't need to be. So for our purpose, as we'll see in the later slides, we'll keep it constant and we'll keep it to be a single qubit. But for like a general collision model, it could be anything. But usually, like if you want it to be like implementable, then you'll like work with a smaller environment.
Right. And but so it's just I would have imagined that it also facilitates the analysis, but you're saying it's purely based on implementation. because of implementation reasons is why you're restricted to constant qubits and not mod general model. Is that right?
Right. So basically, it's giving you two different things. It's giving you a implementable picture and also a macroscopic picture of like how an uh, open quantum system could evolve. Right. So
And is it general enough to capture like every Lindbladian, or it's a specific case of the Lindbladian dynamic? Probably.
So as I'll show, it is general enough to capture Lindbladians and probably more. So like the collision model cause it's like I did not uh, put any restrictions on what things could be. I just did a discretization. So it is in general more uh, like yeah, it is more generalized than Lindbladian dynamics, and it encompasses Lindbladian.
But even with the constant qubit size, you're saying it encompasses
Yeah,
Lindbladians.
yeah. So for our case, I'll describe what the unitaries are. So we need so in general it could have three parts. So one is the system Hamiltonian, how the system will evolve. The environment Hamiltonian, the evolution of the environment part, and then the interaction part. So and this gives me a total Hamiltonian, and I can write the unitary as a Hamiltonian simulation or the uh, Hamiltonian evolution of these system, environment, and interaction Hamiltonians. Now, the good part, as Atul was pointing out, is the
Before you go on, I have another silly question. As on the
yeah,
previous slide, you have a Hamiltonian for the environment as well. And I suspect, okay, this is different, right? But for the cases where the Lindbladian works, you were saying that somehow we assume that the environment is memoryless. So does
yeah,
that essentially mean that the environment Hamiltonian is like identity or something, or because otherwise it would
exactly.
have memory.
Yeah, so I like in later cases, I'll take the environment Hamiltonian to either be identity or zero, or I think it depends on like so basically I'll take the environment and its Hamiltonian in such a way that the environment state is always stationary.
But you're not making that assumption here in the interaction model. You're keeping it more general. Right?
Yeah,
Okay.
yeah. So right now I'm just describing the general collision model.
Got it. Thanks.
So yeah, so when we come to like when we reduce the or like put some constraints on collision models, we end up getting the Lindbladians. And specifically these constraints are the interaction time needs to be small, the coupling needs to be strong, or it needs to be inversely proportional to square root of interaction time. And this third assumption called zero mean assumption. It basically means that in some sense means that environment doesn't change much, and it doesn't there's no uh, evolution of the environment part. So what I will do is take the discrete collision models. I'll put in these assumptions, and then we'll recover the Lindbladian from this. So what one can start with is take the evolution unitary, and I'm taking Taylor expansion of it up to the second order. And then I can put this Taylor expansion in the single collision map and I'll collect some terms, and on putting the zero mean approximation, I will be left with only two terms. So the first term becomes the uh, unitary part, and then the second term gives the Lindbladian or dissipative dynamics. So right now it doesn't look like a Lindbladian that I had described, but uh, I will like generate a Lindbladian out of it. So what uh, I yeah. So what I will do is I'll choose my interaction, or I'll construct my interaction Hamiltonian from the jump operators that was provided me.
I have a question.
Did you unmute?
Yeah. So in the previous slide, we had this assumption, right? Like trace of environment, like H interaction, like the commutator of H interaction and rho S tensor rho E. Like, what does that assumption intuitively mean? Sorry, I missed. I think you mentioned it earlier.
So this is a assumption where like the which is the like zero mean, or like basically the environment doesn't evolve kind of assumption. So
Okay, yeah, good.
Yeah.
Thank you.
and by choosing the interaction Hamiltonian of this form, so basically we have jump operator tensored with a raising or lowering operator. So it's a like block diagonal kind of matrix. And then by choosing my environment to be, let's say, 0, 0 state, I can recover the exact Lindbladian kind of dissipator. And so this is only for the one jump operator, but I can basically repeat this process again and again. And this will give me the complete Lindbladian with a minor tweak that because I'm applying this map multiple times, I'll also get multiple unitary terms, which we'll have to eliminate by rescaling the system Hamiltonian. So what our collision dynamics now become is we have a short time interactions. Let's say if you have a Lindbladian with M jump operators, then you'll have to do M interactions and then repeat it again and again. And how long does one environment interact with the system? So we can control it via parameter nu. So like if the total evolution time is capital T, I've divided it into new separate collisions, and so each collision takes place for T by nu times. And so if you repeat the overall thing nu times, what one will get is a evolution for the time capital T.
So just to quickly do a sanity check for myself. So if we do not have, say, any coupling to the environment, right, the system is just evolving under its own Hamiltonian, then the collision model is essentially this discretized time evolution, unitary time evolution, right? Like you're evolving with certain delta things. Is that correct?
Can you repeat? So like if you don't have the environment Hamiltonian is what you're asking?
Well, okay. Let's say I don't have the interaction Hamiltonian.
Yeah.
Okay, if lambda
Then
is zero,
it becomes a unitary dynamics, right?
so it's a unitary dynamic, but in the collision model, it would mean maybe I'm missing some steps. So because even the Hamiltonian, the unitary evolution is being done at discrete steps, right? Do I understand that correctly? With every collision, you're doing a unitary evolution, right? Even though the collision is
Right.
kind of meaningless because there's no interaction, but
Right. But then it will become some kind of Suzuki Trotter formula or something. So basically,
exactly. So it reduces to that, right? That's all I'm checking. I'm
yeah,
just doing the
yeah,
sun.
it does.
Okay.
Yeah, it does.
Okay, thanks. Yeah.
So to summarize, what we have done is first we have shown that under these assumptions, in the instantaneous limit, the collision model dynamics is same as the Lindbladian dynamics, or if I take limit of interaction time to be 0, I'll get the Lindbladian. And then to actually do the simulation, what I can do is take tau to be very small and then repeat the process. So in some sense, numerically integrate it over simulation time capital T and get the complete dynamics with some approximation which depends on how small you take your interaction time to be. Right. So the question is like, how small do you need to take this? So it has been shown that the error between the collision model under these constraints and the Lindbladian dynamics scales as 1 over nu, where nu is the number of collisions that you take. So so basically your interaction time was capital T by nu. So overall, if one can, let's assume, simulate one collision, then to simulate Lindbladian dynamics with M jump operators for time t. So capital gamma is some energy scale, some simplifications we did to make it look prettier, but it basically describes the energy, like the maximum energy scale of both the Lindbladian and the system Hamiltonian. And so one will need to take the order of some t square by gamma epsilon number of collision steps to have a epsilon close approximation of the Lindbladian dynamics. Now, this gives you an method, but it's still not. It is still not end to end. So, like, if I stop here, like, you still can't go and run the simulations, or like you can't code it up. So, in the next.
So sorry, I didn't understand what the issue was. Say it again. It is not end to end because what?
So it still depends on how one gives you the system and jump operators, and how will one simulate the collision step. So basically, it depends on the how one will implement the Hamiltonian simulation, right? So this is not the end-to-end complexity.
Okay.
There is
You're
a
saying that it's missing the complexity of the collision stuff.
right.
Like you're just saying it in terms of the number of collisions, but the complexity of the collision step needs to be added. Is that what you're
Yeah.
saying?
Yeah,
Okay.
exactly.
Thanks.
So from here, we'll develop a end-to-end framework for simulating such kinds of dynamics. So first, I'll define an input model. So I'm assuming here that the Hamiltonians and jump operators are given to me as a Pauli decomposition with polynomially many terms, and then like same as the derivation, I'll fix my environment to be in a single qubit 0, 0 state. I can choose my environment Hamiltonian such that the mean zero mean approximation holds, and I use the jump operators to construct the interaction Hamiltonian. So
So just a quick clarification. So here, do you require that the Hamiltonian is local in the sense that the number of non-trivial operators each term acts on is constant as the system scales, or you can have non-local Hamiltonians as well.
You can have non-local Hamiltonians. It's just the Pauli decomposition of it should have only polynomially many terms.
Right.
Otherwise, like
But otherwise, you can have like very long range interactions. Okay.
or there is one caveat here. Like even if your decomposition has a lot of terms, if you can provide me some way to sample terms out of it efficiently, then also we are good.
So it could potentially be, like, for example, if I give you identity, then you can obviously uniformly sample any Pauli, and that's fine. So
Yeah.
that would not have a, like a. No, actually, that would just be one. No, anyway, what I understand. Sorry, carry.
So once I have the collision Hamiltonian, what we need is the unitary operator or the time evolution of it, and we will use the LCU method here. So what we are doing is we are taking the evolution unitary and we are approximating it with the LCU decomposition, where the LCU terms are easier to implement. So such decompositions are like possible, and I'll just like refer to those works. But for our case, the unitaries, or the LCU terms becomes the simple operations that one can perform in a typical quantum hardware. So what we get is a sequence of Clifford gates with a single Pauli rotation, and this is repeated a couple of times, and the number of times that you repeat describes your approximation error. Now, using this decomposition, I can create a distribution from which I will sample the terms. So let's say your interaction unitary has some over alpha jwj decomposition. I'll normalize the probability, and then based on it, I can make a probability distribution. So the wj with bigger alpha j will have a bigger chance of getting sampled. And more importantly, if I take multiple samples, the expectation value of this decomposition will tend towards the actual unitary that we want to implement. So what it provides us with is with a simple circuit or a randomized circuit, which you can run multiple number of times, and in the expectation value gives you the collision model dynamics, or in our case, Lindbladian dynamics. So what I'm doing is we have a 3 register. First, I start with preparing it in the system state. Each environment I initialize again and again in some initial state, for our case, which is 0, 0. And then there is a ancilla register which I keep in the plus plus state. And what it gives you is the with with probability half, you'll have the x1 applied, and with probability other half, you'll have y1 applied, and both y1 and x1 are sampled from the distribution that we have created. And now we can repeat these. Yeah.
Sorry, when you say they're applied with probability half, I suppose you mean they're applied coherently, right?
Correct. Yeah.
So it's okay. Yeah. Okay.
So now, if each collision basically then describes one. Sorry, each block here describes one collision, and after each collision, I trace out the environment. I prepare a new environment, and then sample from another distribution that I created from the second interaction term, which is constructed from second jump operator. And I repeat this m times, and then repeat this process total new times to get the overall evolution. And then I measure on some observable O to get the total expectation value.
Right. So I think you already mentioned this. Sorry for the interruption. But these row sub EJs are all 0, 0, right? Like initialized to 0.
Yeah.
Is that?
Yeah.
Is
Like
there any
it
reason
doesn't
why
need to be 0, 0, but 0, 0 is good enough for us. So it
But I thought in the
basically,
LCU decomposition you took it to be 0, 0, no? I thought all those
Yeah.
results held for.
yeah, but one can just like change it a bit and still get the Lindbladians. So like so what 0, 0 does here is just take one like the topmost part of the matrix. If someone uses let's say some other 0, 0 plus some alpha 1, 1 state, you will get contributions from the second part also, but then you'll maintain the Lindbladian picture, but then you'll get multiple, like so each for each jump operator you'll get 2 terms, and then you can play with how much it is 0 and how much it is 1 to like get a slightly different Lindbladian.
So wait, but yeah, I think I missed a few steps at some point. So given a Lindbladian, wait, so okay, so you'll have to, or maybe I can ask you afterwards. Maybe that's
Okay.
okay. I'll ask you afterwards. Yeah, carry it.
Yeah. So because we were sampling from the distribution that we created from the LCU decomposition, if we repeat this process multiple times, an expectation value, this will have an effect of applying the unitary U. And so overall, we'll recover the collision model dynamics. But with the caveat that we are actually not preparing the state, but we have an estimator which measures expectation value over some observable. Right. So
So the caveat is that it's able to give you results from measuring local operators. So you can sample outputs of measuring local operators, something like this. So
yeah. So the method only gives you a unbiased estimator of some expectation value of some observable. Like you can't have a state prepared.
right. Yeah, that's fine. But and this, what are the restrictions on this observable? Can it be any observable, or is this something that yeah, or should just have an efficient circuit, or I don't.
Right. So what I have ignored here is the measurement circuit for this.
Yes.
So it will depend if you can prepare an efficient measurement circuit for it or not.
So I should basically say that, like maybe in general, if there's a unitary followed by a computational measurement, if you can prepare an observable of this form, then using this procedure. Is that right?
Exactly.
Okay.
So
Okay.
one. So there is a some hidden cost which we have ignored. But like if you go and implement this, you'll also have to maybe assume that your observable is also given as a Pauli decomposition, and then you will maybe group those Pauli terms and then measure them and then take average over that. So to actually get the expectation of O.
Right. So that's a little bit different, right? Because if is it immediate that if I give you some unitary followed by a computation basis measurement that you can efficiently compute the Pauli decomposition of this? Is it obvious?
Wait, so I don't understand your question correctly. So are you saying that I give you a unitary and if I give you computational basis measurement, can you approximate any observable? You're saying that?
No. So what I'm saying, okay, so if I am, okay, correct me if I'm wrong, okay, so what I understood was that if you have an observable whose Pauli decomposition you already know, right, then it appears that you can apply your procedure and make those Pauli measurements in the end, and then on average you will get it'll basically behave as an unbiased estimator, right?
Yeah.
So this is correct. I was just wondering if my measurement is somehow more general. Like, for example, if I give you the measurement as apply this efficient quantum circuits, I give you like the description of what gate goes where, and then you make a computational basis measurement. So the whole thing acts as some specific kind of measurement, right? And then it's not clear to me whether this new measurement in this the description I gave, from this you can obtain the Pauli decomposition of this one.
I don't think one can. It becomes a tomography problem, right? I think until and unless your observable is some projector or
it is a projector, right? Because you're making computational basis measurements. It is a projector, of course. But okay. So let me ask you a slightly different question. So if I give you a measurement of this form, that there's like an efficient circuit, and then you make a measurement in the end, can you use your formalism with such a measurement, or do you need to have a Pauli decomposition of the measurements? Maybe that's the more appropriate question to ask.
So what the formalism is assuming is some way to measure the observable O, right? So then you'll like if you do computational basis measurement, you'll have to have some method of mapping that measurement outcomes to expectation of observable, right? So that part will be missing, and unless your observable is trivial, I don't think that is possible.
Okay. Yeah. Thank you. Sorry for the interruption.
Yeah. No worries. So, there are two approximations, barring the measurement circuits and all. There are two approximations that are happening here. One is the collision model error or collision model approximation, and then the second is the Hamiltonian simulation error. So, or the error in our circuit implementation of the collision terms, right? And what we have shown is we can make both of these errors arbitrarily small. One by increasing the number of collisions, and second by increasing the number of repetitions in each collision step. So overall, what we get is a estimator with arbitrary precision, which approximate the observable measured on some state evolved under the Lindbladian dynamics. Right. So if I put together all the terms, the overall complexity that we get is one will need to do O square by epsilon square number of repetitions of circuit with a maximum circuit depth of order somewhere around t cube by epsilon. I think I've missed uh, like probability factor here. So like, cause we are like doing a randomized circuit, there will be like this will happen only with 1 minus delta probability, and then the number of repetitions should be of order log 1 by delta something. So I think I missed that factor here.
Sorry. What was beta max? I forgot. Maybe you mentioned it.
Yeah. So beta max is maximum over each like coefficient of the Pauli decomposition of both HS and LJs.
Oh, right. Okay.
Yeah,
So
like
the Pauli decomposition of the Lindbladian, like the biggest term in the.
as well as jump operators.
That's the job. Okay. And T is the time, and M was what? The size of
M is
the
number of
environment?
jump operators.
Oh, the
Sorry?
number of okay, number of Lindbladians, right? Something like this.
Yeah.
Okay. Epsilon is the area you want. Okay, good. And that's the operator norm of the observable, or which norm are we using?
Yeah, it's the operating norm.
It's the operator norm. I see. Cool.
Right. So there are other methods to do the same implementation. So because we have basically the collision model is a sequence of Hamiltonian simulation with repeated like tracing out of the environment in between. So one can use maybe Suzuki Trotter formulas or Q-drift to simulate this dynamics, and we have calculated the complexities if you use such methods. And so here's a comparison. So in our method, we need an extra ancilla qubit. So in total, there are like n qubits coming from the system part, and then we have a single qubit environment, and then another qubit which is put in like plus state and controls the controls and anti-controls the terms that you sample. So we have only considered the so our another main motivation is to build a early fault tolerant algorithm, and what that means is we want approaches which are relatively easier to implement and doesn't need a lot of extra resources or fancy techniques like, let's say, QSVT or block encoding. So our input model was simple. Our technique doesn't need any extra fancy stuff, and so we only considered Hamiltonian simulation techniques which fit that bill. So compared with this technique, our single ancilla LCU approach gives a quadratic advantage over at least first order in Q-drift, and also second order trotter. But if you go to a higher order trotter, it gets better and better. If you compare time, the second order trotter performs slightly better. And our method is same as Q-drift and first order trotter. Another advantage which we share with Q-drift is the complexity doesn't depend on number of terms in the Pauli decomposition of the system and system Hamiltonian and jump operators, because we are like sampling from the distribution. We're not like simulating each term separately.
So just a quick question. So all these other algorithms, do they also do the state preparation, or do they only give sort of expectation values for observables?
Yeah, so this is one caveat of our method. So the other, if you use other techniques, you can do a state preparation.
I see. Yes.
but with losing the benefit of this quadratic advantage, and then
Right. But like second order trotter, for example, continues to give you like state propagation.
sorry.
The second order trotter continues to give you the ability to do state
Yeah,
propagation.
yeah.
Okay.
Yeah. But thing is like at most like if you go to a higher order trotter, it becomes more and more complicated and harder to implement. So people like at least in
The circuit
Hamiltonian
gets deeper.
simulation, uh, I think the third or fourth order trotter becomes the most optimal, and if you go to even higher order trotters, you actually end up losing uh, the advantage.
I see. I see. Um, and when you say it's harder, because the number of qubits is still n+1, so when you say harder, I guess the circuit is deeper.
Yeah,
Like you
yeah.
have to apply
Circuit
more.
becomes better. Like asymptotically, it becomes better, but the coefficients blow up.
Or the constants are here because the circuit that you've already written. Okay.
Yeah,
Okay. And the tilde is hiding some log factors, I suppose.
yeah,
We can also improve the dependency on epsilon, right? So if we use some classical post processing and like
right.
recharging
I'll come to that. I'll come to that.
Okay. Yeah.
Yeah. So we performed some numerical simulation. So what we took is a transverse field Ising model with the amplitude dampening channel attached to each spin. So it's basically very simple and like toy model kind of stuff. Like most like simulation algorithms like test their simulations on these kinds of models, and what we achieved is so we compared the C0 gate count of our circuit with different level of precisions, and we found the our method, which is the single ancilla LCU, performs significantly better. So this is for a fixed time with t equals to 1. So there's at least like 3 order of advantage, and at least in the C0 gate count. If you compare, like if you fix the precision, if you change the evolution time, it performs better than the first and first order trotter and Q-drift, but with the higher time, the second order trotter end up getting better results, and it also can be seen in the asymptotic.
So the C0 gate count and the depth are not the same, right? Yes. It's not necessary.
It is not the same, but it is a like in most cases the C0 becomes the most costly thing to implement. So it captures the complexity, or like the actual implementation complexity, pretty well. I think one can also compare T-gate count, but I think you'll get the similar result.
So you're saying that's a numerical result because like you looked at that specific thing and instantiated it and counted the number of C0s? Is that?
Yeah.
Okay. And of course, you don't necessarily have a closed form solution to this because it would depend on the Hamiltonian result.
Yeah. So I'll also talk about some recent advancements that have happened and some future directions. So anything I say after that, like please take with a lot of salt. Like these are just like my thoughts and my ideas. And so first is the like obvious question of like, can we do better? So right now, our algorithm roughly has some t cube by epsilon scaling of the circuit depth, and which is kind of far from like at least like some known lower bounds. So can we do something to reduce this gap? So I've been
So
thinking
what are
about
these
this.
lower bounds? Sorry, sir. What
So-
are these lower bounds?
So
Yeah.
this lower bound actually I directly took from the Hamiltonian simulation. So like Hamiltonian simulation is like a sub problem of the Lindbladian simulation.
Uh-huh.
So at least like for Hamiltonian simulation, it's proven that this is the best you can do. So
So how do you get
there
access
is
to the Hamiltonian? Because like you have a very different access model, right? Like for you, I thought you said, oh no, you were saying you can sample the. Yeah, okay.
Yeah.
What is the query model for these lower bounds for Hamiltonians?
I think it assumes a like oracular model where like you have a block encoding of the Hamiltonian, and then you can maybe use that oracle to perform a like evolution. I'm not 100% sure, but like yeah, these are based on the qubitization and QSVT. So I think yeah, they use the
Okay, I also don't
oracular
know
model,
much.
but I think there's a reduction of it to basically I think decomposition or like gate-based model also.
But in like sampling based techniques, I think the complexity more or less depends on the order of t square. We can go to t if we do Suzuki order and those kind of things, but in most of the sampling based algorithms, the dependency on time is of the order of t square, I guess.
He's not about an algorithm, right? He's talking about a lower bound.
Yeah, like most of the like in cases like Hamiltonian simulations, if you also do Hamiltonian simulation using sampling based methods.
Mhm.
So in our paper, like we have shown that you cannot do better than t square.
So you're saying that the lower bound can be strengthened
Yeah,
at
yeah.
square, you're saying.
Mhm.
Okay.
You can go to t to like do full non-randomized version, but since in this model it's kind of very similar to randomized technique, so
Yeah.
I don't know.
Yeah. You for the randomized approach, I'm pretty sure you can't go better than t square. So recently there has been some work which I think Soumyabrata was also pointing to. So you can improve the scaling on precision from 1 by epsilon to log square 1 by epsilon. And so what one uses here is interpolation or extrapolation techniques. So if you, I'll go back to derivation slide, and if you look closely, this structure is very similar to what one get in a Trotter decomposition of Hamiltonian simulation, right? So and here the nu is replaced by like the number of collision in like Hamiltonian simulation becomes like number of repetitions, like the time step, like size of your time step that you take, right? So like earlier in like 2024, people have suggested using polynomial interpolation for Hamiltonian simulation. So what one do is choose different time steps and then extrapolate it to taking infinite time steps. So for each value of let's say nu, I'll compute the circuit. I'll get a scalar observable like measurement out, like measurement over some observable, and then I'll do this for multiple different values of time step. And in the limit nu approaching infinity, I know that I'll get the exact perfect solution. So what one can do is like fit a polynomial to these uh, the measurement outcomes that you got, and then extrapolate it to zero. And if you choose the sampling points carefully, one can show that you can boost the precision exponentially. So it takes you from log 1 by epsilon, sorry, 1 by epsilon to log 1 by epsilon. But with a caveat that now you don't have a state prepared. You only have an estimator. So recently Momadipur and Shiantauli extended this approach to Lindbladian simulation from Hamiltonian simulation, and they've achieved exponential improvement here. There might, so this only improves the scaling over the precision, but there might be, so like similarly coming from the analogy with Suzuki Trotter formulas and Hamiltonian simulation, you might be able to prepare, let's say, like higher order collision models. So I don't know, it's just like random, I'm not sure if this approach works or not works, but maybe you can do a higher order collision model, which is a better approximation of the Lindbladian dynamics, and maybe improve on both time and the precision vector there. Um, so pointing out again, so another motivation was to have a early fault tolerant algorithm. But in our work, we have only covered the early fault tolerant parts from only one perspective of algorithms. Like you can only get a complete picture if you also focus on the fault tolerant part of it. So how does this framework or method pairs with the error correction technique? Can I use some particular error correction which performs better with these techniques, and does it also help in mitigation, or is it like robust against some noise, and can I do some better compilation techniques because we have like very specific kind of structure. So all these are questions one can poke and get a more implementable and maybe more near term or like early fault tolerant picture of where we are sitting, and how actually how hard is it to do these kind of simulation, and maybe bring it even closer to point at which we will be able to simulate these. The third extension that could be possible is we have only covered the Lindbladian dynamics, which is although very commonly used, but also very restrictive. So can collision models simulate other kind of open quantum dynamics, and how close that approximation will be? So these are the some questions people can ask. So in our work, we did cover the non-Markovian dynamics, which is very simple and constructed. So what we do is after each collision, so instead of one environment register, we keep two environment register, and after each collision, we couple the environment register together. So what it does, it adds a memory effect to the dynamics. So this is just a way of showing that collision models can also do non-Markovian dynamics, but we don't know what in physics, what kind of dynamics this kind of collision model approximate, or so. And so collision models are very versatile. So maybe you can add more environment ancillas, or maybe change the couplings and do some engineering there, and maybe simulate other interesting dynamics there. Another part is there's a limitation to our work that we are only sampling. We are not preparing the state. So does it mean that can we use it as a subroutine in other algorithms? So as I had said earlier, the Lindbladian dynamics people are using for other kind of algorithms. So can we plug this formalism there? So this is unknown. And moreover, like can collision model also do state preparation? So actually, this problem has been resolved recently, and there was a recent work by Jianding and um, other collaborators, which uh, proved that the collision model with some specific interaction Hamiltonians can also get you to the gift state. And we like last month, like we had honor to have a talk with Jianding, which like showed this method. So um, this is one direction where there has been some advancements. So this is the last direction I have. So what I have described is a method to simulate some open quantum system, but what we and like most people in I think quantum simulation are struggling with is like what actual quantum systems to simulate. And so like if you are so there are two questions, like is your quantum simulation better than classical methods, and uh, is your quantum simulation actually useful? And it has been pretty challenging to find systems where both the things are true. So either if you're try to simulate things which are uh, have practical applications, there are classical techniques which are also doing pretty well. So tensor networks, DMRC, and density function theory or stuff. And then if you try to show the quantum advantage, most likely it becomes very contrived type of systems which you have engineered. And so like, it is good to show advantage, but it doesn't have any utility. So with this question, I'll end my talk, and these are some of the works that I cited.